In this work, we contribute a general and practical framework for casting a Markov process model of a system at equilibrium as a structural causal model and carrying out counterfactual inference. This work is accepted into the proceedings of the NeurIPS conference in 2019. Markov process models, also known as stochastic kinetic models, represent complex systems as discrete components that interact in continuous time, and where interactions are stochastic and governed by natural laws. Like causal models, you can use these models to predict the effects of interventions. They do so by direct stochastic forward simulation. A typical use case is that as a modeler, I want to use a Markov process model to predict the post-equilibrium behavior of the system upon an intervention in order to select interventions with high predicted utility. An alternative modeling framework, structural causal models, or SCMs for short, enable counterfactual prediction of post-equilibrium intervention outcomes. For example, you can ask the question, conditional on an observed intervention outcome, what would that outcome have been under a different intervention? This enables counterfactual off-policy evaluation of intervention selection policies, a technique that's growing in popularity within the reinforcement learning community. Also, by predicting interventions in a way that is conditioned on observed data, you make modeling more robust to model misspecification. In general, structural causal models of equilibrium lack the Markov process model's description of mechanism. Markov process models predict interventions using stochastic forward simulation. However, simple stochastic forward simulation won't work for predicting counterfactuals. A main contribution of this work is an algorithm for converting a Markov process model into an equilibrium SCM that retains the Markov process model's mechanistic elements. We demonstrate the approach on two mathematical models of signal transduction pathways, the MAPK signaling pathway and the IGF signaling pathway. These models can be downloaded from systems biology websites and compiled into Markov process models using software such as MATLAB or Capacity, or libraries in R or Python. We contribute an experimental design that introduces a technique for simulating artificial counterfactuals from the Markov process model and comparing them to counterfactual inferences from the derived SCM. We use causal effects as a metric. A causal effect means differences between an observed and a counterfactual intervention trajectory post-equilibrium. This figure illustrates histograms of causal effects for the MAPK signaling pathway model. The SCM's distribution has less variance. This is due to the fact that the SCM's model of intervention uses do calculus-style ideal interventions. This model of intervention has less variation than the more typical way of modeling interventions with a Markov process model. Results also illustrate how using counterfactual inferences with an SCM makes intervention prediction more robust to model misspecification. The left shows results from the MAPK signaling pathway model, and the right comes from the IGF signaling pathway model. These histograms show causal effects over several iterations of the evaluation. The ground truth causal effect is indicated in orange. The green corresponds to a causal effect predicted by stochastic forward simulation from a misspecified Markov process model. That same misspecified model was used to derive an SCM. That misspecified SCM was used to estimate the causal effect indicated by the blue histogram. The blue histogram of predicted causal effects from a misspecified SCM is closer to the orange histogram of true causal effects than the green histogram of causal effects derived from a direct simulation from the misspecified model. Finally, we implemented our code in the PyTorch-based probabilistic programming language Pyro. This is a novel implementation of counterfactual reasoning using structural causal models within a probabilistic programming framework. All code is available in GitHub.